Okay, this one is on. So recording is on. So first thing which I wanted to talk about is this poll. So like I sent an announcement on Piazza, I forget when, like last week. But essentially, we discussed briefly in class if Thursday at 4 p.m. works for the office hours. People said yes, but then some people say no, it's not ideal. And I think at the moment, like, okay, what is it? How many? 10 out of, okay, 10 of just 11 people filled in the poll. So if you, I mean, I'll go off, like I cannot make sometimes, like I cannot get the time after the class because I have to run. But like Thursday and Friday, especially this block, which looks really green. So can you guys participate, and then I'll pick the time which works best. Otherwise, you know, like we can do something at home. We can also do like a slot which is in between. Just concentrate on this. I mean, Tuesday is ideal for me, and Thursday, Friday, because here I teach, right? And after the class, unfortunately, I have to run these 2 days. But other days I can stay. I can even stay at like up until 6. I don't know if I open up the slot, but it's fine. So just fill in, otherwise it will be hard. And I'll do them in person in my office most of the time, but there will always be Zoom. Last time there was a Zoom, but maybe I forgot to advertise it.
Oh, I was just gonna say, yeah, if we're not on campus Tuesday, but that time works, I think we just ask for Zoom, right? That's fine.
Yeah, no, but there will always be Zoom. But if there are people in person, then it's easier to prioritize them, right? Okay, cool. So the second thing is the auto grader, which we just discussed. I mean, it's a really simple one, but and Soham agreed to help. And but the idea is to just get the same environment, like install the Nix shell. And I mean, it's not that I can create a lot. And don't worry if you don't pass it, just let me know, and I will take a look manually. But the idea is that it kind of builds whatever does make run or whatnot command similar to our build environment. And then we'll just check for QEMU, we'll check that you mapped the 4 gigs of space or whatever I ask, probably 4, right? So, and then supposedly it's very easy, but then it kind of makes life a little bit easier for us. And I guess I didn't do that, but Soham will help. Okay, so that's coming. So yeah, so I apologize for the delay. Any other administrative issues? Did I forget something? Oh, good. Okay, so I wanted to come back to the interrupts. So because we have to like make it concrete and essentially just figure out how to program this thing. So last time I spent the lecture discussing how the interrupts work in general, right? And like at this point, you should, yeah, like if I show you this picture, right, you should immediately come back and say, yeah, remember what's going on. What's important here is again those data structures which are this clear, right? So it's and those are the data structures which we have to initialize to get interrupts and exceptions booked. Right? So you need essentially a global descriptor table, interrupt descriptor table, in a task state segment, right? And they're connected like in some weird way. So the hardware sends you an interrupt number. It doesn't sound so. Just follows the program. We say the hardware processes an interrupt number 32. It has an interrupt descriptor table register, which points to the interrupt descriptor table. Interrupt descriptor, it chooses the entry number 32 in this interrupt descriptor table. From there, the connection to the GDT is that you can specify a different code segment that allows you to switch the privilege level, for example, switch from user and go back into the process the interrupt in the car, right? So for that, you need to create a GDT, and we'll talk about it today. But essentially, you have to set up like a kernel code, kernel data, user code, user data, and DSS itself, because when you switch into the kernel, you don't have a stack because you don't cross the user stack because user ESP can point someone on a page and will trigger a second, like a double, right? So you pick up this stack from the TSS and the connection here, which is not on the speaker, but the GDT will contain an entry which points to the location of the TSS. And then TSS itself will point to the stack. And that's kind of the cost, right? And that's what we discussed last time, and we talked about that. By the way, I mean, we kind of like talked about what kind of flavors of exceptions are there. So some of them are synchronous. That's where you're like dividing by 0, for example, or invoking an int some number instruction, right, which triggers the synchronous transition for the IDT. Synchronous interrupts cannot be masked, so they cannot be disabled, right? They are always happening. However, there is a protection mechanism. For example, in the interrupt descriptor table, you can specify which of those interrupts the user or which privilege level can invoke. So that's why user level can invoke into X40, for example, to implement a syscall. It's not involved in 32, not pretend that it's a timer interrupt by invoking a software instruction, right? And what else? So that was important. And last time I was asking, look, guys, there is this weird convention that actually the stack looks different on the interrupt transitions. But let's come back to this in a second, right? Any questions about this diagram?
So generally, we would have to look at the hardware, all of the exceptions and supports, and then build kind of sort of a plan. Like it would, our handling would be hardware.
What do you mean? What do you mean? Like between the architectures?
Like a 5x0, for example.
Yeah, it will be slightly different on other platform, or might not even exist.
Right. Okay. So as an OS developer, you have to look at the hardware and have it separate.
Right. And I mean, like, since we're doing this, let's quickly, I forget exactly, probably have the code opened, but just a sec, Intel. So the way you go about it is that on Intel, you search for this, and on other architectures, it's kind of a similar name. So, or you can ask a search engine, what this one, like, hold on, let me switch it off. What is it? Disable this. So, like on Intel, this is their Intel software developer manual. Like it has, as I said, and I mean, I forgot exactly how I first came about to know where to look. It was years, and if you ask me, okay, what's the manual for ARM or for RISC-V? I don't know it, so I have to like look it up. But the idea here is that it has multiple volumes, and this volume 3 is a systems programming guide, and that's what I open here. I mean, it's written in such a manner that it's not a pleasure to read, right? So especially from the first time, but if you understand what you're looking for, then it gets easier. And so, for example, it has an overview with all these registers, right? So, for example, when you know this stuff, it kind of makes sense. But if you don't know this, these pictures are just like kind of confusing, right? It requires prior knowledge. But for example, here they show interrupt descriptor table register points to the interrupt table. Interrupt table connect you to the like choose an entry from the global descriptor table. Global descriptor table has this TSS pointer points to the task stack segment, right? From here, they can you can pick a different stack and stuff like that, right? But there is also some cases which I don't even explain, and for some cases which I don't even know myself very, very well, right? And so it gets a little tricky, and they have this chapter on memory management overview where they talk about segmentation and paging. But suddenly, you know, like it's all 32-bit paging, and paging was, segmentation. And segmentation was largely disabled on 64-bit machines, right? So go figure. And they had a couple of intermediate modes of execution like this 32 extended mode, And it gets kind of annoying, right? But that's the idea, and that's like a final document which tells you how it's supposed to work is this manual, right? And so other architectures, they have a similar set of features, but slightly different. So that's why in a Linux kernel, there will be a giant hardware abstraction layer which abstracts the architecture. And then at some level, there's some kind of like, you can register a user interrupt handler in the kernel, not user, a kernel interrupt handler through this abstraction layer interface.
But the vectors can change from.
Yeah, completely different. Yeah, everything is different. And so wait, hold on, like one thing which I wanted to like show is that this is the current mapping of those reserved entries in the global in an interrupt descriptor table, like the ones which we looked before, of course, are not changed. There was a couple of new ones, like which I didn't have on my slides like this 20 is a virtualization exception. It's like EPT violation, extended page table violation. What is this 121? I don't even know. It's for the Intel's shadow stack violation. Essentially, it's a technology which allows you to protect the control flow. Okay, this was the question, right?
Yeah, this was like I've seen this table before. I was just asking for
for other similar features, but vectors will be different. Everything will be different. Layouts of data structures will be different. Even some set on like.
So to make like a long-term operating system, put special effort into creating that abstraction.
Correct. Yeah. But
so as a future developer, I just have to make a handler for segmentation calls. I know that they are.
Correct. Yeah, but I don't, that's so true, right? But at this point in time, probably just concentrate on understanding.
Yeah.
Generalizing, it's not sugar, honestly. Like in Linux, it's layers of layers to the point that it's hard to read the Linux code. So it's so abstract. And it's hard to actually figure out which implementation is used because it gets compiled and there is layers of macros and everything. And then you don't even know which code gets compiled. So sometimes it's easier to disassemble and then see, okay, what is really going on. But for now, let's just concentrate on one. Okay, but the point I brought up this manual. So I probably will I will put the chapter names or section names in the assigned reading, and hopefully I don't expect you to read it or know it or anything. Just essentially when you start working on your next homework, it crashes, you don't know where to go. I mean, you first start searching on Google. That's totally fine. ChatGPT, totally fine. If you get help, then sure. But then sometimes you have to really carefully read those lines and say, and like, it's kind of crazy, right? Like the level of details. It's not always easy to understand, but you can still read. Okay, any other questions about this interrupt transition? Like, I just wanted to make sure that we first understand how it works first, and then let's work through the details. High level is clear, right? We understand synchronous, asynchronous, interrupts can be masked with this on Intel is called CLI, clear the interrupt bit, E flags register, STI, set the flag, right? But there is one non-maskable interrupt, which is this interrupt number 2, right? So which is delivered even if you disable the asynchronous interrupt, it's always delivered. However, the second non-maskable interrupt will not be delivered until you process the first one. That's the logic. So only one of them will be delivered, and then you have to acknowledge it through the interrupt controller, and then the second one will be delivered only after that, right? Okay, so this is cool. So now let's make sure that we understand how to write code, right? So again, back to this previous figure. So this is what we need, right? We need at least these data structures. So global descriptor table, just because, I mean, it's a good question to ask. So why do we need them? Like, it's on the slide, but do we understand? It used to be that segmentation was fully capable, right? On 64-bit machines, it's actually like it's reduced to almost nothing. I'll come back to it in a second, but on 64-bit Intel machines, the base and the limit of a segment are always 0, right? Or limit is like the max address space, right? So my question is like, do we understand why we need to go over the table?
So that it could be backwards compatible.
Almost, but no, always. Not actually, it's not even backwards. Like these are two reasons, right? So I named it here. So first of all, we still use it to configure privilege levels, so we can transition between. And second, one entry is used to have a pointer to the TSS, right? TSS we need. Why do we need TSS? To have a pointer to the kernel stack, while some other stacks we'll talk about them. But essentially, that's the reason why we need TSS. Drop descriptor table, a contain pointers to the drop handlers, with protection mechanism. We allow users to involve in 32. And we need a kernel stack. Right? So, but that's kind of the minimum. Maybe I missed something, but more or less, this is what we need, right? So, okay, so again, what is this GDT? So GDT is the data structure in memory. So again, this is a picture from the Intel developer manual. So here they list two tables, global descriptor table and a local descriptor table. And this TI flag actually decides which one are you using. We're not going to use local descriptor table, so forget about it. Just make sure that the TI is set to 0, right? But essentially, it's just a region in memory, right? Pointed by the global descriptor table register, which consists of two parts, the base of this table and the size, which Intel calls the limit, right? And essentially in your homework, remember, we created this funky data structure, which contains the address of the global descriptor table plus this. It was an assembly, so it was hard to read. You can do the same. And we loaded it with a load GDPR instruction in memory, right? And so now the question is, okay, in order to load something, we need to create this table, right? Let's take a look at what's inside. What is this each entry of this table, right? And each entry is called this segment descriptor, right? Which is kind of funny because you say, look, first of all, this is the entry from the 32-bit machine. So it did not change from what I taught in my x86 class, which uses 32-bit architecture, right? Intel didn't change it either. They say, okay, sure, we just leave it like this. But in 64-bit mode, by the way, segmentation is almost nothing, right? So all the bases are assumed to be 0. So you can only have zeros here in the base in these two fractions, right? Sorry, 3 fractions. And a limit is always maximum address space. So how many Fs you can put into this 64-bit address space, right? So those fields are kind of like ignored by the hardware, or hardware will trigger a general protection fault, I think, if you misconfigure them. But certain fields are still used. So this descriptor privilege level, which sits here, is a 2-bit field, which encodes the privilege level and allows you to transition from ring 3 into ring 0, right? Because your interrupt descriptor table entry will choose an entry in the global descriptor table, like one of these, and this one will be configured with DPL 0, right? Which means that your code will be running later after that. After this transition, it will be running with current privilege mode 0. So you switch from 3 to 0. L is used, and L means that it's a 64-bit code segment, right? So where is L here? This one. So this has to be set. And type is used as well, so which allows you to configure executable or data segments, right? So if I remember correctly, those are the only 3 fields which need to be configured. Everything else has to be set to some default values, right? Make sense? Like, again, as I said, like normal segments like DS, SS, ES, they don't have bases. However, Intel, again, says, okay, guys, still have something for you. So they said, like, these two segments, FS and GS, are allowed to have a base, non-zero base, right? However, those two segments they are not loaded from GDT, right? You can configure them explicitly by writing those values into model-specific registers. What is model-specific registers? It's, again, roughly speaking, a configuration space which Intel exposes to you. You use an MSR read and MSR write instruction to write them. So it takes a number of the register, and each register has a specific meaning, right? And so specifically, there is a register number, MSR number, this one, and it's a FS base, and this is GS base, and you can configure them to be non-zero, right? And then if you write your code, and like if you have something like a move instruction, and you're using something like GS 00, for example, if GS has a non-zero base, then of course this base gets added to 0, and everything gets shifted in your address space. Do you guys remember how we use GS and FS segments, and why Intel keeps them around? Nobody knows? Well, nobody ever disassembled code with GSFS. Okay, first of all, there is like, Intel doesn't tell you. Typically, they are used for thread local storage, meaning, right? Like in C++, you can, I forget exactly the syntax, but you say something like thread local, right? And you say, look, and I apologize for the syntax. You say something like thread local, and you say int a, right? What does it mean? There will be an instance of this a variable in each thread, and it will be a thread local, meaning that if you create two threads, T1 and T2, there will be two instances of this a. So there will be one a and another, right? And like it can be implemented differently, but an efficient implementation will use this address GS a, address of a, and GS will be pointing from the beginning of this thread local area. A will be an offset here. If you have another thread local B, there will be another B allocated here, another B allocated here, right? Essentially, the runtime, when you initialize the language runtime, every time you create a new thread, it will allocate a region of memory, and you say, okay, this is your thread local storage, and it's very fast to access because it takes you like the same cycle as the regular access, right? So it doesn't have to get, you don't have to go through some, like, if you don't have this infrastructure with the GS, then you can build your own kind of like hash table style thing, where you say, look, my thread ID is 0, 1, please resolve me into this address, right? But it takes additional time. And so efficient implementation is to use one of these GS or FS, right? So when you see it in your code, it means that it's thread local storage. Make sense? We'll come back to it. And the second thing which we will be using in operating systems, right? Operating systems also execute on multiple CPUs. And we will be using this trick with GS and FS for CPU or per CPU local storage. It's the same idea, but imagine you're running on a specific CPU core and you want to know the value of the pointer to the currently running thread. Obviously, this current, and the current is a canonical name to point to a thread. And thread, what is thread? Like some data structure in a kernel which represents a thread, right? T1, T2, like whatever, current working directory, whatnot, current address space pointer to the current process here, whatnot, right? And of course, current is different from CPU 0 and CPU 1. And we'll be using the same GS or FS trick to say, look, for per CPU data structures, we'll create, essentially, when we initialize our environment, we'll create, if you have 32 cores, we'll create 32 instances of this thread local or CPU local data structures, right? Makes sense? So that's why those are there, and they're used on Linux. I forget exactly. Linux uses one of them for the per CPU storage, one for the thread local storage for user level code. Make sense? Okay, good. Any questions? So these two, that's why, and there is like there is an instruction swap.js. We'll come back when we will be building system calls. Okay, cool. So then this is clear. So one question which I wanted to ask is that what about TSS, right? So for all these segments, I said, okay, the segment and the base are ignored. The limit and the base are ignored, right? So you don't really have to change the number of bits you allocate for the entry in global descriptor table. Remember that TSS actually has a real pointer. So TSS, like here, if you have a TSS entry, it will be a pointer to where the actual TSS data structure located in memory. So this one will have a base, right? So how do we solve this problem? Because normally the segment descriptors, like the total length is 64 bits, right? We just need 64 bits to have a 64-bit address pointer to the TSS in memory. So what do you think Intel is doing here? Well, it's impossible to guess. It's just I wanted to emphasize that, everything else, like all the other code data segments, since most of the fields are ignored, format did not change. There's still 64-bit entries. For TSS, Intel says, okay, really, I need to put a pointer, right? So, and it just doesn't fit. There is no space to put a 64-bit pointer, right? So they created a special format for this, for the TSS entry in the GDT. It's double the size. And that's the latency, essentially. It has enough bits to put like this. Okay, look, you have 32 bits in your legacy 32 bits, but then add more, and that's total 64 bits to point to anywhere in memory to figure out where the TSS is located, right? The other fields, I think, if not identical, they are very right? So just remember this, that all the entries in the TSS in the GDT will be like 64 bits, but the TSS will be special. Will be 128 bits. Make sense? And the reason is that you need to put a pointer there. Okay, so we got the TSS, and then last time I was asking, okay, how we solve this? So we have GDT, we have TSS. Do I have the IDT? Jesus, I probably didn't. So let's quickly go about. I probably didn't make a slide discard. So let me just quickly go to the Intel manual to show you the format of the IDT. It's right here. So where is it? So I would assume somewhere here, interrupts, exceptions. And again, this is what you have to do. Like every time you program, you at least have to like scroll through this document to figure out what is the entry. Exception, interrupt handlers. I got stuck on the stack. Where is it? Okay, 64-bit mode, right? So it only starts at 7.14. So the chapter 7 is all about interrupts, but only 7.14 starts talking about 64-bit mode. And this is essentially the same idea. They ran out of space because you need a pointer. It's a most step. In the end, that's why they extended double the size, and so the upper. But this part allows you to put a real point to anywhere in 32-bit address, 64-bit address space. So on that, agree? Any questions? Right? So far, so good. And this is where we left it last time. So it's still, even in 64-bit mode, every time you receive an interrupt, you start on a new stack. I mean, hold on, like not like that. So let me ask you, when are you starting on a new stack? Do you remember, guys? Okay, what's the story about the stacks? Tell me. How many stacks thread S. Thread of execution, Q1. How many stacks? 1, 2. So I'm graduated 1. Okay, why 1? Well, logical to expect that it has 1. So 1 thread of execution, right? So ESP, when the thread is running, points to some location in memory, right? Okay, so on why 2?
Kernel stack if
Kernel stack is what?
kernel stack if it's needed,
If needed.
like for these situations. Needed, I don't know.
Well, yeah. Imagine a timer interrupt 32 arrives while you're running at user level, right? We cannot, in the kernel, we cannot cross the value of the ESP because it's user control. User could just say move ESP to point to some page in memory, which is not mapped, and then it's a double fault, right? Agree? Or yeah. And so for this purpose, essentially, we configure the second stack in the kernel, right? And every time the interrupt condition preempts execution of the thread at user level, right? It's T1. Again, like not surprisingly, hardware looks up interrupt descriptor table, like in my figure. From here, 2 parts. 1 points to the handler, like essentially, which will process interrupt number 32. This will allow you to choose a code segment in the global descriptor table. Right? The reason is that you were running in ring 3, you want to switch in ring 0 to process an interrupt, right? And this one will have a DPL field set to 0, right? This is a code segment, so that you switch from 3 to 0. And finally, you say, look, since I don't trust the stack, ESP can point anywhere, use this is the code segment, this is the TSS entry in the interrupt table. The TSS, this is a code segment entry here. And this is a TSS entry, and TSS entry will point to the TSS table, and TSS table will contain a pointer. I'll use a different color, which will contain a pointer to this kernel here, kernel stack. Make sense? That's what I was trying to explain all this time, right? So there are 2 stacks. Every time you create a thread of execution, you allocate two stacks. The second stack is used for serving interrupts. Since the kernel controls the TSS, it has like RSP pointer. That's my RSP, and it knows where the stack is allocated.
The reason you drew it like that, going back to those are Intel. Why don't you draw
No, it's just the layout questions. There's nothing specific about it. I should probably throw it around like this. Sorry. Yeah, it was, I apologize. There is no intersection like this. But this is what's important, right? And this stack, we know that it exists, right? Because we configured it when we started the thread, we exited into the user level, and we know that the moment interrupt arrives or the thread just does something funky and there is a page fault or something, there will be a kernel stack, which is allocated for this thread, and the hardware will be able to push some information on this kernel stack and start executing of the handler in the kernel, right? Make sense? Okay, so we have two stacks, right? Now the question is like, okay, what's gets saved on the kernel stack? So if we have a privilege change, right? So the hardware pushes this, Jesus, I did upside down. The bug actually. Let me cross check. My intuition was, yeah. So that was upside down. So if we had to essentially at the very top of the stack hardware, which is stack segment, stack pointer, E flags, hold segment, instruction pointer, and for some exceptions, it pushes an error. The hardware fills in the numbers, the page hold, you do that really. So this 5 or 6 things will be pushed on this kernel stack, right? Agree with this? Right here. If we start running the interrupt and another exception happens, right? And we are already running like inside the kernel, inside the like handler, exception handler, which is already running inside the kernel. At this point, a slightly different thing happens, right? So the hardware says, okay, I do the same transition, but since you're already in ring 0, you're already like, we're not gonna like erase everything from this stack because obviously we want to preserve it. And assuming your ESP was somewhere here, because you already pushed something inside the handler, you push something on the stack, right? Because you started executing some functions. The hardware will push some additional things on this stack, and in this case, it will not push the stack segment and the stack pointer because those didn't change, right? And so it will just push those either 3 things or 4 things if you have like an error code, right? And this stack keeps going, right? And obviously, if you're receiving interrupts very, very frequently, you may run out of this space, right? So you have to think about how you make sure that you don't run out of this stack space, right? Or if you're clever enough, maybe you can grow it, but in Rust, it's probably possible. In C, it's hard, right? Okay, makes sense. And so let me quickly, what I want to do next is just show you some Rust code for how to encode these data structures. What you're saying is that, hold on, maybe I misunderstood the question. So ask again.
So is it possible to store the address of the kernel stack in some protected memory?
So for example, you say, look, this is an address in the kernel, like a global variable, right? Which you say, look, we'll point it here, right? You also say, look, what if I very carefully construct the code of my handler in assembly, that nothing gets pushed on the stack, but you just kind of like move from whatever this pointer is, like, let's say kernel stack, move an address of a kernel stack or variable into the ESP, right? Or like RSP, initializing the kernel stack and keep going. After that, you have a stack after this first instruction, and you push more stuff on the stack, right? That's a good idea, and it would be kind of elegant. You say, look, I initially have a tiny stackless trampoline, which allows me to set up execution environment for the handler, because I know that like the couple of assembly instructions don't really require touching the stack, right? So it would be a nice thing, but however, why it doesn't work immediately. So unless you change the hardware slightly, why do we need the stack immediately before we even start executing this very first instruction of this handler? Entry point is in the interrupt descriptor table that points to the handler, right? Entry point of the handler.
It needs to push something to the stack.
Okay.
That's what
Yeah.
I'm saying.
What is it? When you say, what if it needs to push something? What is it?
Local variables.
What?
Local variables.
Well, it's assembly. There is no local variable. You control what you want.
Well, I mean, it does have to push that stuff.
Correct, right. So because we are immediately losing interrupt flags, because we say maybe in the IDT there is a flag which says, okay, further interrupts are disabled. We are losing the old value of the code segment, which was like entry in the global descriptor table code segment, but it was PL3 segment, for example, or maybe it was PL0. We didn't know where we were running, right? So we have to, hardware has to save it. We need instruction pointer, obviously, and hardware also pushes error code, right? Essentially, the interface between the interrupt handler and the hardware is such that this gets pushed on the stack. You can say, look, that's a little ugly. So can we change the hardware to have something like 6 different temporary registers, something like SS hold, ESP hold, E flags hold, CS hold, EAP hold, error code hold. Okay. Hardware just simply saves those 6 things into those registers, and we here establish the stack and essentially start pushing them on that stack, right? That's okay, almost, right? Why is it almost okay?
What if it gets interrupted before it does that?
Correct. So what if it gets interrupted somewhere here? Because we said, okay, we not always want to have interrupts disabled immediately, right? Sometimes we keep them on. You can probably play a game saying the interrupts are always disabled for this short period of time and explicitly re-enabled, which would be a fair hardware design, honestly, right? Like maybe it would, like it's a great question. Like, is it a better choice versus the idea of maintaining the kernel stack in some awkward manner through TSS, or just like setting up stack manually makes sense. So for example, if I remember correctly on ARM, and I'm not an expert because I didn't touch it, unfortunately, but I think it has 2 stacks, explicit ESP for the user and ESP for the kernel. And just, you don't have to look it up, it's just there. You don't have to go through all these tables. You just say, look, when I switch the privilege level from user to kernel, I will use and I will push on the kernel stack, right? And then that may be a more like elegant design, honestly. So because you don't have to go through those data structures, right? Make sense? Any other questions? Okay. Yeah.
I'm a little confused. So
Yeah.
ESP pointer, isn't that for the user space stack?
This one, ESP,
Yeah.
on Intel is just one register, right? So the Intel doesn't distinguish between user and kernel registers.
So
You
this-
have to maintain them like in software. On ARM, there is a separate, if I remember correctly, there is something like ESP. ARM inverts the rings. So 0 is the least privilege, if I remember correctly. And there will be ESP, something like, let's say 3. And you switch between the rings, but those things, the operating system configures them, and they point to the correct things.
How does ring 0 use this one register? Is it the same way as it's ESP pointing to the user?
Just it's a pointer in memory where the runtime of the language configures to be the stack, right?
Yeah, so why are we saving ring 0? Like, does it ever get overwritten during
No.
recurrent ring 0?
Well, yeah. Wait, hold on. That's important. So it immediately gets overwritten, right? So if I were to make a note of the state of hardware registers, let's say yellow. Let's imagine we have, this is like CPU. Hardware registers, let's say RIX, all of them, RSP stack, RBP, but doesn't matter, right? This, when we were running at user level, this was pointing right in here, right? When we go through the transition, right? We pick up the stack from the TSS. So the hardware pointer gets, instead of pointing here, it starts pointing here. But hardware pushes 5 things on the stack. So this guy will be pointing right after the 5th thing, right? Or right below.
So we push the old version.
Yeah, we push the old version here, RSP user. Or not we, but the hardware does, right?
Yeah.
Makes sense? And you know how the stacks are maintained by the compiler, right? So like calling conventions.
How would you go about testing?
What do you mean?
Like, how would you go about testing that your setup?
That's what
Like, how would you test? I guess that the interrupt after the interrupt without like a user process. User. How would you test that this is the kernel stack is handling pushing all of these together, like networks?
You mean, I mean, like, it's a very like overloaded question because, and I don't fully understand it, but because the first thing to figure out is what is that you want to test? What is correct here? Are you talking about the hardware
order that you're pushing all of these.
or whether it's reordered in hardware? That's a great question. Intel just declares that they will do it correct, right? You ask yourself the question, okay, do they always do it, right? Maybe there is some kind of like very awkward state in which silicon makes a mistake, and instead of like, if we get solution steps, for whatever reason, maybe there are some, you know, if you look at the Intel manual, there will be pages and pages of specs, what's supposed to happen on every instruction, right? You ask yourself a question like, you guys, like, are you sure that you do it correctly, right? Or maybe there is some corner case which you just blindly forgot to do it, right? Or maybe this works and something else doesn't work. It's some other transition. Like you screwed it up, and it happened in like it happens every so often. They screwed up floating point computations. I mean, of course, they screwed up side channel attacks, right? Was always like, you know, you can read memory about the processes through side channels. That's slightly different correctness. But the question is like, how do you even test that CPU is correct? And I think this is the area which is still under investigated, honestly. So we trust Intel. They do some testing, supposedly. They test their silicon, they test their models. If we, as offensive attackers, we should generate like a ton of false testing, for example, and like whatever, initialize our registers with some values, trigger an interrupt, see that they are saved in the correct order. But you ask yourself the question, okay, well, sure, it will work because it will give the test. Can you fast test all of it, right? Or something, right? It gets tricky, and there is no easy question. I don't follow the literature in this area, but you can imagine that you like with any fast testing, depending on where you are in this, you say, look, I will describe the CPU as a state machine. I will see which states affect this transition. I will randomly target transitions which are kind of lead to this state, and maybe I will find a bug. And people did find bugs or undocumented features in Intel CPUs and other CPUs as well. It's an interesting problem. I'm not an expert. An ideal solution for a computer science student with a good kind of like horizon is to say, look, guys, we're not going to trust Intel. You guys should go to hell. We will build our own CPU. Like it will be completely open. We'll write a formal verification framework, and so on and so on. It's tricky, but this is the future essentially. We do trust Intel too much, and certain things Intel does not reveal. And like again, side channels were the biggest kind of. You guys like majorly screwed it up, but there is more. That's any other questions? But blindly and in this class, we just trust the stack. By the way, one interesting observation here is that we will be running on top of QEMU, right? So we're really trusting not the Intel, but QEMU implementation of and versions of QEMU and different like QEMU versus a box, it's a different emulator versus something. They slightly sometimes screw up because the Intel documentation is so weird and giant, and it's very hard to get right. They don't release you like a formal spec for the CPU. They just write this awkward manual, which they update every other like whatever 3 months or 4 months. And sometimes the links are broken, sometimes something else is broken. So don't be surprised that QEMU can get it wrong. It typically works, but like new features, it can get it wrong. And vice versa, if you completely don't understand what the CPU is supposed to do, like how to configure this EDP, for example, it's sometimes easier to read the QEMU source code than Intel manual and say, okay, look, I get it. Like on this transition, this is what the CPU is supposed to do. You guys read it. And I mean, we were doing it with my students, like read the QEMU source code just because we were not able to set up a specific feature. Okay, good. So, wait, almost there. Okay, so last time I asked how to write this in Rust, but before starting with this specific thing, let's just take a look at how to write certain things in Rust. Rust is actually quite like it's quite a nice language, right? And the code is not mine, so it's written by Stefan, my PhD student. He is a. If you look at my code, you can. It's called Redleaf, right? So I wrote parts of Redleaf. You will be like laughing and like my code is ugly as hell. His code is nice, right? I have a couple of slides and then we switch to like to essentially to the GitHub or something. Okay, so no, first first let's define what was the right? Again, a good question here is that what is the minimal GDT, right? What is that we need to put there? So let's quickly think before we read through the code. Like what entries in the GDT are needed for us? Because even if you start reading Philip's blog, I'm not sure I understand what Philip writes there. So he starts the kernel in such a manner that it never exits into user level. Or at least I didn't see it, like which is a little awkward, yeah.
I have a more fundamental question
Yeah.
about the GDT and the DSS.
Uh-huh.
So is the GDT processor specific and the ESS thread specific? Like every new thread will have its own DSS because it needs its own kernel stack.
Okay, great question.
GDT and the IDT would kind of be.
Okay, yeah, that's a great question. So who knows the answer? Like the question is like, is it per core or is it like one global or per thread or per core or per what?
I would assume per core for at least the GDT. The TSS would probably be for like logical.
Yeah, and you're probably kind of right. So, and again, I'm pretty sure that different constructions are possible, right? So, but let's just take a look at what's needed. It's a great question. So, GDT conceptually has a pointer to TSS, right? Yeah. And TSS has a pointer to the stack. That's how we view it, right? So obviously, if there is a thread running here and there is a thread running here, then we need two different stacks, right? So because it's like thread one, stack one, then if it's thread two, then we need stack two, right?
Yeah.
At this point, we say, look, how can we make two different stacks? If they don't work, a stack is pointed by the TSS, which needs like a TSS. Okay, let me just redraw it like this a little different, like right a pointer to stack. And of course, TSS doesn't exist in the air because the way the CPU accesses it is through GDT, right? And yes, it has a pointer to TSS, which leads us to this kind of, okay, sure, it at least GDT is per core, right? So at like this is like parallel execution on two different cores, right? And so we need those two things to be different, right? Well, now at least we say, look, GDT will be per core, TSS. At this point, it's a design choice, and you say, look, every time I switch a thread from T1 to T2, for example, I really, instead of like switching this pointer and having a new TSS, I can just switch this pointer. Like so TSS stays, and we just change this field in the TSS and switch to stack 3, right? Or whatever, stack 3. Make sense?
Yeah.
And so this way, the stacks are per thread. So it's thread 1, thread 2, thread 3, right? The GDT and a TSS can stay per core with the assumption that we will be overload, like changing when we switch from T1 here to T3 on this core, then we will change this pointer to a new stack, right? What if you go, when you switch back from T3 to T1?
Yeah, but I still need.
Yeah. So this area is allocated per thread. So like the way we're going to build the kernel is that we will have like the list of threads. Sorry. So let's imagine a list of threads, like it's thread 1 on this list, thread 2 on this list, thread 3 on this list. Those are just data structures like C style or Rust style. Here we'll have a pointer to thread stack, and here we'll have a pointer to thread stack, which is over here, stuff like that, right? And T3 will have a pointer to this stack, right? Makes sense? So this is the data structure, and when we do a context switch, we'll look up these fields in the thread data structure and like update the TSS field to point to this stack, right? The question is like, will it ever happen that we will be halfway and something is on this stack and we are switching away, and when we come back, we obviously want this TSS to point to here or where? It's a great question. And I think there are different design choices how to do this. So I think XV6 never allows you. No, actually, XV6. XV6 allows you to do a context switch away from a thread, and they save the ESP register, but they know that you're already like this value of ESP will be saved in some field here, right? I remember, yeah, like there's like a context field and stuff like that, right? But ESP will be saved, and the TSS will be always loaded to the top of the stack. But since you're running in the kernel, you're already at level 0, ring 0, which means that if a new interrupt arrives, the hardware will push here, so you don't have to really come back to the beginning of the stack. But like, I don't want, okay, even looking at you, I already see that it's confusing. So forget about it for a sec. We'll come back. It will become clear. I understand that it's a little unclear right now. It's just too much to unpack to understand what's going on here.
So each thread has a TSS, which has a pointer to its stack along with.
No, look. We agreed that these two can be per CPU.
Yeah, yes, so.
Per core or CPU, like whatever, or.
So when we switch from a different thread, does that mean, because the TSS also stores other registers in it?
No.
It's just a pointer.
Yeah. Like TSS was a field which was used for like a ton of different things on Intel. Right now, we only care about one or specifically two fields, which is a smart pointer to a stack. 2 because it has stack segment and actual stack pointer.
So why does the GDT point to the TSS if the TSS is just?
Intel told us that's how they designed it, because
So couldn't you just store it in the GDT?
that's a good, like, in a way, yes, but the hardware is not designed this way, right? There are partial reasons for that. There are different reasons for that. The reasons are that Intel allowed different transitions, and there is like a ton of different stacks here, not just this one. Like there will be a stack for different privilege levels, and which are typically not used, but there is also something what is called interrupt stack table. There is like a collection of other emergency stacks. We'll come back to them, and they are saved in the TSS as well.
I see, so there are a couple more things.
Yeah.
Like miscellaneous things that are also switched when we switch.
Yeah, sometimes you switch them, sometimes you don't,
I see.
like depending on like how you structure your kernel.
So it's more useful for it to be structured instead of just throwing it.
That's debatable. Like everything is debatable,
Yeah.
but this is how Intel built it, and that's how we use it.
Okay.
So, just want to make sure.
Yeah. Yeah.
It's like.
Yeah, to some degree, but how often you go through an interrupt? Like,
I don't know.
yeah.
It's also.
I mean, these changes are also happening every time there's a time interrupt in a context switch for.
Correct, but still, like a typical in a practical system, the duration of an interrupt is roughly like say 10,000 cycles. That's the shortest. Linux cannot even switch in 10,000 cycles, so it takes long. Like a good system will switch in something like 800 cycles, right? Like the microkernel which we're building. For Linux, it's like tens of thousands of cycles, and you're saving roughly like one cycle. You can say, look, what if it's like a cache miss? But those are frequently accessed data structures, so most likely they are cached. You can like run a user code which evicts the entire cache just accidentally or maliciously on purpose, or just because the working set is giant. And then you will just pay the flat price loss if you reach to third level cache plus 50 cycles. If you reach the memory, then like it will be plus 250 cycles on. So it's there, but it probably in practical terms, it is never on your critical path. Right, so that's okay. Although that's a little, I agree, it's a little awkward when you walk these data structures, but in practice, it's probably doesn't. It's not a problem. Any other questions?
So I'm trying to understand, okay,
Uh-huh.
just to make sure I understand. When we switch threads, we need to store, or when we get interrupted, we need to store all these, like a certain set of registers. Are we pushing it to its own stack or to the kernel stack?
Kernel, just because we don't trust, like if we have, again, coming back to this diagram, like set of CPU registers here, ESP. User can override ESP, you just simply write a code of assembly, or just ESP can point to nowhere, right? Which immediately, like hardware says, okay, look, I'm trying to push something on the stack. I walk the page table, but it's not mapped, so it's a double fold. You're trying to do it again, but it's again unmapped, and so it's a triple
Okay,
fold
so that happens during interrupt.
transition, right?
This is a little unrelated, but when threads switch, like if we had a scheduler, is its personal, like RIX, for example, are those stored in stack? So is that?
Yeah. No, like here, yeah. So again, different constructions are possible. We'll talk about it when we get to context switch. Roughly speaking, you can either push them on the stack, on the kernel stack.
Oh, kernel stack.
Yeah, no, because the context switch is in the kernel. I mean, you can implement user threads. I don't want to, again, like, because people then complain that, okay, the guy always like goes and talks about something, right? But
Oh, are these talking about threads in the freezer?
yeah, okay, we'll come back. But yeah, there is a certain gap because you didn't take the x86 class. But people who took x86, they kind of hopefully know. But
Sweet. Thread.
no, one kernel. Each thread will have a kernel stack and a user stack allocated, right? Roughly speaking, right? Or you can save those registers as part of your thread data structure. That's okay too.
That's what's done next.
x86 actually pushed them on a stack. The context in x86 context lived on a stack. And I think I assigned either a homework or something saying, okay, put it on the somewhere else, and then let's see how the kernel needs to be changed. Any other questions? Yeah.
The threads.
When, by what?
You said you can also store.
Here, or in user level, when you build the user threads?
Yeah, the thread data structure. Still these were the thread, the stack for each individual thread. That's what I call it.
Yeah, this is on the kernel heap, right? It's like,
Process heap.
it's all in the kernel, like all of these data structures are in the kernel besides this yellow part, this hardware silicon, right? TSS, like it can have a pointer to user stack, but we don't use it. It's like specific transition. In Intel, there was another interrupt like mechanism which could transition you from the kernel to the user. Rarely used in practice recently, but maybe it was used. Okay, so good for now. Okay, back to my question. So I answered yours, right? So it was about what? Stacks and data structures. It's a little hard to, like, I get it. Like I explain it, you probably will forget. When we code the kernel in the homework, there will be more. I don't think I will provide an argument, but there will be like a declarative statement saying, okay, DDT is per core, and don't forget. Right, but essential reason is that those run on two different cores parallel in physical time. So like anytime interrupt can happen, anytime you have to traverse, the hardware can simultaneously traverse those pointers on both cores. Like it's clear, right, that interrupts can happen. The cores are individual in terms, like separate in terms of interrupts, right? So you disable an interrupt handler, it only you disable on one core. Other cores receive interrupts, right? It's just everything is like parallel. Okay, what are the minimal entries in the GDT? What do we need? Okay, that's how we ended up asking about it. Yeah, what are those entries? Yeah, TSS is there. Yeah, we need TSS. What else? Kernel stack inside TSS, right?
Oh, well, okay.
Yeah, so TSS, entries in the GDT. TSS, what else?
The spoilers are on.
Yeah, I know, don't tell me, like, decode this slide. Yeah, okay, let's keep everyone in mind. Edo says there will be null entry, which is not used. Sure, so it's now really like zeros. But then you need these two pairs. Kernel code and kernel data. These two will encode privilege level 0. Every time you start running in the kernel, you use these two. And you need a similar pair for the user. User data, user code, privilege level 3, right? If you want more privilege levels, again, used rarely in practice, but still occasionally used in some research systems, then you add more of this stuff. This is kind of the minimum, plus PSS. That's more or less the minimum GDT, which you have to create on 64-bit hardware to get like both user and kernel code running.
So even your, like, if there's a context switch from process 1 to process 2 on the same code, we'll be changing the GDT entries for this.
Good question.
I do.
But do we need to change user code and user data? Let's just quickly recall what's in this entry. Sorry, this one slide. Oh, so lots of tiny little fields. These three are important. Okay, let's read this slide. Base is 0.
Oh,
On 32-bit hardware, if you use segmentation to switch, then you change. Right. In x86, you don't. That's all. In x86, anything base is 0. And that's what inspired Intel to remove segmentation, because no one was using it for real. And they said, okay, no one is using, but our hardware team is so busy testing because it introduces so many corner cases. I'm not kidding. It's most likely they officially called the fact that it's complex design part of test. So base is 0, limit is max, no changes, right? Privilege level is 3, no changes. L is still L, is 1 or exact stages. We don't have to, right? So the only thing is to change the base. Either change the base of the TSS if you want to switch like that, or if you follow this pointer and change the stack pointer here, then you won't get it. Like either of these two. That's your choice. Make sense?
Then have to like save the user process segments on disk or.
Okay, that's a great question, but remember the hardware pushes them for us. Every time we transition into the kernel, and this is your kernel stack, right? The hardware just pushes this for us on the stack, right? This by field swap narrative, right?
The hardware does that?
Yeah. So this,
Yes.
yeah, by pips, yeah. So this is pushed by the hardware, and for us, it's again it's a choice. We can either keep it here and just remember we saved it there and access it later, or you can move it somewhere else if you want. Like if you have a thread data structure, then you can save those here. But typically, it just stays on the stack. No one bothers. Make sense? And that's why when we exit, when we do an IRET instruction, which is symmetric to interrupt entry routine, IRET essentially looks at those. The stack has to be pointing to this 5, right? And then it just restores those and switches back, right? Okay, so so we got it. So this is our minimal GDT. Like there's this packed attribute, say that okay, it has to follow this layout. As I said, all the entries are 30, like 64-bit entries, but one is 64-bit entry, right? So this is for TSF. Oh, sorry, no, this. That's okay, how we define them again. So BDT entry follows the layout, limit, offset, whatever, offset low, offset medium, some offset high. Like literally follows the layout of the entry in the Intel manual. Similarly, for this one is a little more, like it's a little larger, but here we have this explicit reserve to make sure that this is not lost by the compiler, right? Okay, so that's kind of like nothing is super cute happened, so that's expected. So similar to how you derive this copy clone debug traits. So like everything is kind of normal when you work with these data structures, right? The beauty comes a little later. So let me start on this, and then where is it? For example, maybe this. It's a Docker setup. So it's I don't know how to actually go about it. So I need your advice on this one. So there is certain beauty in how Rust allows you to write this code. The question is like, to what degree, how much time I have to spend on it, right? What I wanted to show you, for example, this. So like essentially working, like when you have those definitions of the data structure and like essentially you can create, you can write a constructor, and this is cute because it uses this bit field macro in Rust, which essentially says for this data structure access byte, we will, for this field, for example, present, which is stored in bit 7, we will generate an getter and setter. So there will be like a real method which sets this bit, which is like a lot of automation. So it's all like macro based and auto generated for you, right? So this privilege is a 2-bit field. So you use bits 6 and 5, like again, 1-bit field, stuff like that. But essentially this generates you those getters and setters, and what allows you to, for example, when you generate this access flag here, you can say something like, give me a new access thing, and this is this setter, like set privilege to 0, so you don't have to like write your own logic for how to set up those bits, set executable to true, set read write to true, and then use a entry constructor. And essentially this essentially my GDT, where is it, like I should say Jafunc, right? So like where do we get the GDT from? Like we get it from the per CPU data structure, and I have to talk about how to build those per CPU data structures. But essentially here, there is enough enough magic here that he says, okay, I'm getting the per CPU data structure from the CPU, I'm getting my pointer to my GDT, and here I'm initializing specific field of this GDT, which is kernel code, which is like we had kernel code and kernel data. So the difference here is that this one is executable is true, and for this one we don't set executable true. We have set privilege to 0, right? Because we want it to be like what I wanted to show you here. Just a sec. Pick it up. Wanted to go back. Oh no, sorry. The GDT is defined right here. So just give me a sec. GDT entry, where is the definition? Somewhere here as well. Oh, like here. So access is one field, right? But it's a bit field, right? So if we like, let's take a look quickly here. Where's my entry? This is for TSS. So like this one, right? So access is all of this tiny bit fields is essentially access, right? Like if again, if you follow, so you say, look, limit low, so limit my limit low is here, then offset low, this is my low offset, then offset medium, this is my offset medium, like it's 8 bits. Access are the next 8 bits here, right? And flags, what is it? Flags and limit are here. And then my offset high is this one, right? And so essentially this, the bit field crate allows you to elegantly kind of access, generate like setters and getters for this, right? And then everything kind of like converges together nicely. You say, look, I generated GDT entry. It has a long mode bit, this L bit set, right? Access is configured for read write executable privilege level 0. This is a base and a limit, if I remember correctly, although probably double check. Yeah, base and the limit. For data, almost the same. For the kernel privilege level 0, read write is true. Long mode for the user, the only change will be that the privilege level will be 3. Again, user data privilege level 3. This one is executable. This one is only read write. For TSS, it's slightly like more involved, but we have to follow the code, but we'll see how it works, right? So, but essentially it's a pointer to a stack, to the TSS in memory. And then we load GDT by essentially this get pointer thing will, this is also cute because it just, remember this load GDT is this funky smart pointer, right? Which has a offset, like a limit, the beginning of the global descriptor table, and then, oh, sorry, the base and the size, right? And we create this descriptor and return it from Rust. But essentially, this is also kind of cute that you like created here, right? Makes sense. So my question here is that how much time I have to spend on like talking about those, like my plan was to highlight some of these which deserves to be highlighted. So the code is written by the Funk. I think he looked at what Philip wrote and maybe like cleaned it out, maybe took some way. But essentially, it kind of like looks like a high quality code. Maybe there is a better way to write it in Rust. I mean, my level of Rust doesn't allow me to like come up with a better. So I want to highlight some of it, but I don't want to spend like a ton of time. But my question, like this time, next homework, I will say, look, I'm not going to give you this code, so you will have to write it yourself. The request still. I will give you this of this code as part of homework assignment. Ask you to stitch it together. So how?
One thing I noticed was that the TSS was using privilege level.
Yeah, okay, TSS.
Like back in the first. Towards the end.
Yeah, when we initialize it. So we say privilege 3. Ah, Jesus. I remember this question. I don't remember the answer. I should look it up. Yeah, there was something why it has to be 3. Maybe to enable transition, but I can quickly ask ChatGPT, but you can also do it. Correct, right? But why would you imagine that only 0 should be able to access TSS? Probably some reason. What is this? Okay, question about Rust. So do we want to look at this Rust, or you guys are capable of looking or figuring it out at yourself?
It would be nice to see it.
Say again?
It would be nice to see it.
Yeah. Okay, so but this level of details is fine. So you like how I quickly went through like talking about it, or we want to, okay, then I'll keep doing this a little bit. And then like the expectation is that of course you don't have to remember piece of this code in a homework. It will be a little bit confusing because it doesn't compile, you have to untangle it. But use the same. Well, you can always look at what Philip is writing, but like I said, I was a little confused. I didn't like spend a ton of he doesn't even set up the DB. That's like user and kernel and TSS, which was a little unclear for me. Okay, so let me stop here and then we'll come back. Remember, my question did not change. So I want to come back and explain how you can handle this variability in this stack layout and how to actually generate the interrupt handler, right? So that's what we will do on Wednesday then. Okay, just then, thank you. I'll